We have now the next speaker to come, and he's actually in the 29th last day of his PhD, so he's taking the last breaths of the sweet air as a PhD student, and I can tell you that because I know how the air feels afterwards. It's also not that hard, not that bad in industry, so you can survive. He will, and I like this title because he is also, as I am, a pedestrian in everyday's life, but today he will introduce us in the benefits of using a lift. Welcome with me from the Max Planck Institute of Colloids and Interfaces in Potsdam. Welcome with a warm applause, Sebastian Ronneberger.
Hello everyone, my name is Sebastian, and let's talk about the benefits of using a lift. So we first have to clarify what is a lift. It's a very easy device. You go in, you press a button, the doors are open, then you press again a button, the doors are closing, you go to a different floor, then you go outside and have a happy day. Of course, this is not the lift I want to talk today about. I also do not want to talk about lift as the apple juice or the skin cream from Nivea, although I might be soon an expert in lift, as you can see here. In my universe, which is also called the lab, lift is an abbreviation for laser-induced forward transfer. So how does it work? Well, we basically have a glass slide, and on top of this glass slide we have a metal layer. It's very thin, and on top of that we are spin coating a polymer. Two questions: what is a polymer? I outsource this answer to my favorite chemist. And what is spin coating? Well, it's a technique where you rotate the substrate very quickly. You put a single droplet of polymer on top of that. Then physics is happening very quickly, and in the end you have a glass slide, which is metal layer, and on top of that you have a very thin layer of polymer. And we call this donor because it can donate something. And then we need an acceptor. And lift is now a printing technique. So basically we put the donor on top of the acceptor, and then we do a defined laser radiation, and in the end we basically transfer material. This is very nice. So what's now the benefit of this printing technique? So let's have a quick comparison. This is the diameter of a human hair. It's about 100 micrometer. You see, I've practiced these slides a lot. And these numbers also verified a lot of times. And you probably also know inkjet printers from your office. They have very special devices because due to physics, you have always this droplet deviation, and they have a limited printing resolution of about 1/10 of this hair. So lift has now the benefit that we are very exact because we can locate the laser on the surface very good, and so we have a very high printing precision. What can we do now with that? We can print QR codes on different substrates, for example. We have QR codes which are macroscopically, but we are living in a world where things are getting smaller and smaller. And so I asked myself the question, can we do these QR codes also smaller? This is easy, simple, you can print single spots. If I would be a mathematician, this would be now the end of the presentation, because in mathematics you cannot generate something smaller than a single spot. But I'm a physicist, and so I found some ways around. And the idea here is called superpositions. So basically, instead of printing one spot, we are printing 4 spots, and you can also give them names. And I decided for 1, 2, 3, 4. And we can now basically print in these different subpositions, have then occupation states, and define a binary code. So what you can see here, it's not a bug in the matrix, so don't call Morpheus. It's just some data written on a surface. The benefit of using a lift is now that we can print with different colors, and so we can increase the data density because we have no mixing of these inks, because they are solid. Now I had this question because I'm more an applied physicist. This unit is very theoretical, so we now have to find a different unit. And the idea is here, 1 byte is 1 character, 280 characters are also known as one tweet. And so last year, I defined this new unit, tweets per fingernail. And it was a very good unit until the point where a guy who has the ability to lift his own car into space, his name is Elon, decided to buy Twitter and renamed it. It's very sad for me because I put so much effort in painting this treaty symbol. But yeah. So now we have written this information on a surface. How can we read this data? And there's no computer program available because I defined this method by myself. And so I decided I can ask the computer for help. But the computer had no idea, and I, as a PhD student, had no time to train him. And so I decided to have a machine learning approach where the computer learns itself. And it works in the following way. So basically, we start with a single spot, and when we have a cross-section across this spot, we basically have a 1D Gaussian curve. It could be also in 2D actually, and in mathematics they see it in this way. But don't panic, it's the only equation we have in this presentation today, and you don't have to remember it because the computer is taking care about it. As the computer now generates random data, this is used for training the model, and in the end the computer gave me an answer. It was not the answer, it was a more suitable answer for publication, of course. So this is now the story of 2D, but actually we're living in a three-dimensional coordinate system. So there was a very famous guy some decades ago who said there's plenty of room at the bottom. So let's have a quick look if Lift can benefit from this room. Here you can see a scale, and here again we have a hair as a reference. And this is a cell core, which is about 1/10 of the diameter of a hair, so 10 micrometers around. And when we now print with Lift multiple layers of polymers, we can actually generate such a spacer. It looks something like that. But we can go also smaller. Think about wavelengths of visible light, 350 to 780 nanometers. We can print with such a defined thickness that we have special colors. It's called thin film interference or artificial soap bubbles. So if someone asks me what I'm doing in the lab, I print soap bubbles in an artificial way. We can also go smaller. For example, viruses have a diameter of between 20 and 300 nanometers. And so I decided to print also a very complicated surface gradient. I'm calling her the Nano Lisa because it has a thickness variation between 0 and 100 nanometer. And the best experiment I did so far is this surface gradient, which has a defined thickness variation between 0 and 15 nanometer. This is hardly possible with other techniques. We can do it at room temperature, no vacuum, no clean room. This is a big benefit of using a lift. So this is 3D, but since Albert Einstein, we know that we are living actually in a 4-dimensional universe. And there are some guys who invented, therefore, 4D printing. Basically, first print something in 3D and then have an interaction with time. This is in 4D printing. This is the first experiment I did with my samples. It was a very, very late afternoon experiment. The general person would call it evening. And I sent this data to my supervisor. And typically I get a very quick response. And I also got a quick response in that case. But this email was empty. So there wasn't any text in it. Instead, there was an attachment. And this was this response. So now there's one remaining question. What about higher dimensions? As I said, I'm a soft matter physicist, experimental physicist, applied physicist, maybe even a kind of engineer. Of course, there are also theoretical physicists, and they work in higher dimensions. I have very big respect for these people, but there's one thing, please be careful. If they ever ask you for your guitar, they might use also strings for their theories. And depending in which dimension they are working or where they get funding, they are up to 26 dimensions. So the big question is now for me, for today, or maybe for the rest of the week, could be Lift possible in 26 dimensions? I do not know, but give me some money and we might find it out. And with that, I want to come to the end of my presentation, and I hope that you enjoyed it, and I'm very sure that the next time you're using a lift, you should take care about laser safety. And then you do not... And with the help of these glasses, you are protected from the high-intensity laser radiation, and with that you can see and use lifts and all its products in our universe. Thanks for your attention and have a peaceful evening.
Sebastian, Ronneberger, thank you very much.